Okay, my dear students, welcome back to the Simple Harmonic Motion lesson. Still mechanics of A-level physics. That's where we are. Now, in this lesson, we're going to look at the terms that we use in simple harmonic motion, and then afterwards we look at the equations that we use. So, what are the terms used? Number one is the equilibrium position. We define the equilibrium position as the point or a position in the path of a particle or a body executing simple harmonic motion where it finally settles when all oscillations are done, or at the end of the oscillations. We are saying the equilibrium position is a point in the path of a particle executing simple harmonic motion where the particle comes to rest. So this is the point in the path of a particle executing simple harmonic motion where it comes to rest, that is the particle at the end of the oscillations. The end of the oscillations. That is simple. That's the equilibrium position. Then the period, of course, this is easy. You remember from O-level waves. Period. The time taken for the particle to make one complete oscillation. Time taken for the particle executing simple harmonic motion to make one complete oscillation. You may leave this out, of course. Time taken for the particle to make one complete oscillation. Then, when it comes to frequency, we define frequency as the number of complete cycles made in 1 second. The number of complete oscillations or complete cycles. Oscillations. The particle makes in 1 second. Makes in 1 second. Then the amplitude, everyone knows amplitude, the maximum displacement of a particle from the equilibrium position. So amplitude, we are saying, is the maximum displacement of a particle from its equilibrium position. So we are looking at the maximum displacement of a particle from the equilibrium position. That gives you the amplitude. Now, having understood these terms, can we go ahead? Of course, I used this model here, simple model. You have a body that is attached to 2 springs. So when you displace it slightly to the left, then you release it, it will start executing simple harmonic motion like that, about the equilibrium point here. So we can always have different models, but I've used this just remind you what we learned in lesson 1. So can we now look at the equations that we use? What are the equations that we use? Remember, simple harmonic motion is related to circular motion in a very simple way. Simple harmonic motion and circular motion, they are related. They are brothers and sisters. So Simple harmonic motion and circular motion. Someone may be wondering, how are they related? How are they related? I want you to know that if you look at the angular displacement, if you have a body that is executing circular motion, we have already covered circular motion. It is executing circular motion. And you look at its angular displacement, the angle that is subtended at the center of a circular path by an arc. The arc length that is traveled by a body. This one, arc length is, and this is the radius r, like that. So this is theta. Now I want you to know that for us, when it comes to, supposing you represent now, look at this, this body is moving like this in a circular path. But if you look at it in 2 dimensions from this side, supposing, actually let me just make a simple illustration. Supposing I have this is a duster, and I'm moving it in a circular path, like this, in a circular path, and then someone comes this way and looks at it from this side. I will just see it moving up and down from this way, but it is executing circular motion. But for me, when I see from this side, I see it just going up. While it's moving like this, I see it just moving up, then down, up and down. So from the other side, I'm able to see as if I just see simple harmonic motion, up and down. But then if you look at from this side, you are able to see the complete circular motion. So in simple terms, if you have this theta here, and then you represent it, we can also represent this theta angular displacement, if you recall very well. Angular displacement, let me not take you back so much, but we had the theta as S over R, and then this I will leave out. My interest is going to be on how this angle will keep varying. Of course, here our interest is going to be, we look at displaced. Here we look at in terms of the time in simple harmonic motion. Or you can look at the displacement. Displacement from the equilibrium position and then the time. Displacement against time. This is displacement against time. Now this time can be written in terms of the angle. In terms of the angle. So we can always write it in terms of the angle. Let me not rush. I will come to the graphs later. I may bring something that may confuse a person. So let's first look at the equations that we use. The equations used in simple harmonic motion. Simple harmonic motion. Now in simple harmonic motion, start with the basic ones. There is this relationship between period and the frequency. That is very easy. You know how it comes about. T is equal to 1 over F. On the other hand, you should also recall that period can be written as 2 pi over omega. You recall this. 2 pi over omega. How do I get 2 pi over omega? You can also write, I think this is okay, you recall that. That in circular motion, we are using circular motion, because in circular motion you can still have simple harmonic motion in circular motion. Yes. 2 pi is the whole theta. Whole theta. We know that time is equal to distance over speed. So in circular motion, we are saying for one complete cycle, the time is the period. Should be equal to the distance in terms, that's the angular displacement, is going to be 2 pi. Theta is going to be 2 pi over the angular velocity or angular speed, which is omega. That's how it comes about. T is equal to pi over omega. Now if T is equal to pi over omega, So we shall use this actually a lot. You can also write implying that omega is equal to 2 pi over t. But 1 over t is equal to f. So we can have that omega is equal to 2 pi f. So we can have this, we can have that. So far those are 3 or 4 anyway equations. But they are all very basic. The most important equations that I want us to know, these are the basic ones. The first one is the one that relates acceleration and the displacement. Acceleration is equal to negative omega squared x. So we need this. This is the most important equation in simple harmonic motion. A is equal to negative omega squared x. Some books don't write A, they write x and then they put this, meaning second derivative. Others don't write that, they just use simple notations. Second derivative with respect to time. So you have this. So, but what we're going to do is to quote it as A, acceleration, is equal to negative omega squared x. So, for simple harmonic motion, where the negative sign means that the acceleration and the displacement are in the opposite direction. So, the negative sign means that the acceleration and the displacement are in opposite directions. Please, this is the most important equation. Any equation that is in this form tells us that the motion of that body is executing simple harmonic motion. We said the omega is the angular frequency. Now we are going to use that to note the second one, which relates speed and displacement, or velocity and displacement, and it is v squared is equal to, so you take amplitude squared into, actually it's not supposed to be amplitude first, it is omega squared into amplitude squared minus the displacement squared, or simply denoted as v is equal to, taking square root, we shall have plus or minus omega into a squared minus x squared. Now this one has to be under root. Any of these two here for velocity. So I will show you how that comes about. And then in terms of displacement, we have, actually let me first make derivations, because I may make a summary afterwards. The derivation for this one is the one which, this is the equation for simple harmonic motion. This is what it means for simple harmonic motion. This is the definition. So that one comes straight from the definition. Now equation number 2 comes from equation number 1. Equation number 2 comes from equation number 1. So we are considering a particle that is executing simple harmonic motion, and it has a displacement x from the equilibrium position at a time t. So I want you to know something. Please note. So we want to derive v squared is equal to omega squared into a squared minus x squared. Please note that the acceleration, please note that acceleration is the second derivative of displacement. Is d squared d2 x dt squared. Okay. Now, if that is true, if this is true, it is also, we want to have velocity. Look at the parameters we're looking for. We want to have velocity. Here we have displacement and time, the variables. So, can we use in terms of velocity? Still acceleration. So also, acceleration is equal to the first derivative of velocity. Of course, A is the derivative of velocity, dv dt. Now this one will work for us because we have the v, but how can we do away with the t? Observe that we can write this as dv dx times dx dt. You see that? I can choose to write, instead of writing dv dt, I write dv dt is here. I put dx here and dx here. So I have dv dx times dx dt. Okay? Times dx dt. What is the rate of change of displacement called? Dx dt. That one is called the velocity. So this can be written as v for dx dt, then times dv dx. So you see now we have acceleration in terms of velocity and the two variables and the displacement. So we are now writing that if the acceleration is equal to v dv dx, can we substitute it here in this equation? Our acceleration now will become negative omega squared. Okay, from here, what we had, where there is acceleration, we are putting v dv dx. So we can say v dv dx is equal to negative omega squared x. Let me use that kind of x. Okay, now, of course, this is very easy. This is very easy. You can now write v dv is equal to, separating the variables, negative omega squared x dx. Yeah? Then you integrating both sides. You're going to have integrate this with respect to v. It is v squared over 2. Of course, plus a constant. But since there are two constants, they will give us a constant. So, pulling out this, you have negative omega squared. And then this is going to be x squared over 2. Then plus a constant. So that's what we have. Now we're going to take some initial conditions. When the particle is at the ends, or simply when x is equal to the amplitude. Remember, once the displacement is the amplitude, there the particle stops momentarily, the velocity is 0. So what does that mean? It implies that 0 squared, that is 0 over 2. Of course, just substituting. Should be equal to negative omega squared. This should be a squared over 2 n plus c. So implying that our c equals to omega squared a squared over 2. See that? So if that is true, to summarize, we are going now to have that v squared over 2 here is equal to negative omega squared x squared over 2, then plus the c which we obtained as omega squared a squared over 2. The 2 goes everywhere and pull out omega. We shall have that v squared equals to, I'll start with the positive side. So I'll have omega squared pulled out into a squared minus x squared. That is how that comes about. Now in the next lesson, lesson number 3, I'm now going to talk about the displacement and then we shall see how it comes about. We do some derivations and start now doing some simple calculations. Thank you so much for enjoying Simple Harmonic Motion. Bye bye. Meet you in lesson 3.